Hi, good evening. My name is Hawileh. I'm a professor of civil engineering at the American University of Sharjah. I'd like to start by introducing my co-authors, my graduate students, Ms. Mhanna, and Dr. Jamal Abdalla, as one who co-advised or co-supervised this work with me. And the title of this presentation is Shear Strengthening of Reinforced Concrete T-beams using CFRP laminates anchored with bent CFRP splay anchors. This is the outline of the presentation, introduction, brief introduction, objectives, experimental program, results and discussion, and conclusion, and a little bit of suggested future topics for research. As you know, that strengthening of reinforced concrete members in shear and flexure is conducted these days by externally bonding fiber reinforced polymer sheets or plates, which are composed of carbon, glass, or aramid, and for carbon they call it CFRP, to enhance their or retrofit them in flexure and shear. Or the columns, especially if they are circular, they will enhance their capacity significantly. So in the past they used to strengthen with steel plates, but however with steel plates you are having the problem with corrosion, and they are heavy, and the FRP sheets are in the order of 1 millimeter, and that can enhance your capacity up to 50 or 80%. So there are different types of FRP laminates, among them carbon, glass, AFRP, BFRP. Today we are going to strengthen FRP beams in shear with CFRP laminates. They have high strength to weight ratio, they are non-corrosive, durable, and they are very easy to install and versatile. You can use them in many or in different applications. In shear, if you want to strengthen, it's like a setup. You have to go like perpendicular to the longitudinal axis of the beam, like here and here. This is like if you want to do it with plating with the two sides, or you can do the URAP technique, which you go around the cross section. And this is like the ideal case in columns where you can confine the four corners like a completely wrapped. So we want to do T sections under shear. We want to get something closer to this behavior by anchoring the sheets inside the concrete. So that will prevent the debonding of the FRP sheets away from the concrete surface, because a typical failure mode that will only utilize 40% of the material strength, that after certain loading the sheets will debond away from the concrete. And this is the shear failure, and this will take it out. So usually cracks at interface will cause the FRP limits to start debonding until the FRP system fails, and this utilizes only 40% of the tensile strength of the sheets. So a proper anchorage of the sheets will delay or prevent debonding, and you can have mechanical anchorage, you can have additional horizontal like wraps, also like sheets, or you can apply, you can add FRP splay anchors. And the topic today is to fasten or to bond these sheets with FRP splay anchors. So this is FRP anchors, splay anchors. You drill a hole, and then with epoxy you install the anchors, the spike anchors, into the concrete. This segment here is called the fan, and this is called the dowel. And the advantage is they have better compatibility with FRP laminates, high strength to weight ratio. Also they are non-corrosive and can be designed to suit wide range of structural applications. So the objectives of this research is to investigate the effect of strengthening shear deficient RCT beams with CFRP URAPs anchored with CFRP splay anchors, and compare the performance of the anchored specimens with that of contour and strengthened specimens, and strengthened and anchored specimens, and then investigate the effect of anchored dowel diameter. We are going to play with the diameter in this study of the dowel or the anchored on the shear strength and ductility of the tested strengthened specimens. Here it is. So basically this is the material properties. These are CFRP sheets and anchors. They are VRAP C200H. The thickness of the sheet is very small, 0.17 millimeter. Their elastic modulus is very close to steel. Tensile strength 4,830 megapascal, and the elongation at failure is around 2%. The CFRP laminates, they have, with the epoxy, they will have a thickness of 1 millimeter. The E will drop, but EA, the elastic stiffness will stay the same, which is EA is about the same for both. If you multiply this one by this one, the thickness by the E, it will give you about the same answer, which is about 73 gigapascal. The E and the tensile strength will drop to 1000, about 1000 megapascal. The epoxy adhesive used is VRAP. Again, this is VRAP. This is from structural products, and I would like to acknowledge the support of structural technologies, like in supporting us with the material and installation of the specimens. So we use epoxy to anchor the sheets. So we have in total for this presentation 5 beams, a control strengthened specimen with URAPs but without anchors, one with anchorage of 12 millimeter in diameter splay anchors, one with 14 and one with 16. Here are the variables. And this is the control specimen. Since we want to investigate the shear performance, the loading will be 1-point loading, 3-point bending, where the loading will be applied here. So one side of the specimen was heavily reinforced with stirrups, so that they want this, so that this side won't fail during testing. So, and this side was left without stirrups, shear deficient. So basically we can find the contribution, how much V sub C plus V sub F will be. So basically we are going to anchor this side of the beam, and this is the cross section. In the T section on the top, you have 2 number 12, and then you have stirrups, and then here, like below, you have 4 number 16 bars flexural. So it was also designed to have high flexural reinforcement ratio in order to enforce the beam to fail by in shear. As you can see here, this is the side that is strengthened. This is the unanchored specimen. This one is the anchored, and here we are going. This is the splay anchors. So this is embedded inside. The inclination angle from the top is 25 degrees. So the angle from here to here is around 155 degrees. The fan length is 100 millimeter, the one that we adopted, and the dual diameter is variable. The embedment length for the incline for this inclination is 85 millimeter. It's very interesting, and the procedure for strengthening is easy. You just drill a hole, and then you punch in the anchors with epoxy until you have a strengthened structure. Show you the preparation of the specimens. These are the control beam, the beam specimen cast in a ready mix concrete. These are like this, the preparation of the URAPs, and you can see them here around. And these are display anchors, where they were like fabricated manually by the labor and the student. And then you put the epoxy, and then you put it inside the hole, and then you are going to have a very nice structure presented here. So this is the experimental program again, and you are just strengthening for one side of the beam, and you are applying one load in the middle. We put here like an LVDT to measure the deflection of the specimen. So the recorded data will be the load and the midspan deflection. In addition, we put strain gauges in the middle of the strip here to find the strains in the FRP sheets, and to see how much we utilize in terms of capacity of the CFRP URAPs. You can see here this is the experimental failure modes at failure. These are the beams at failure. For the control beam, it failed by conventional diagonal crack at about 45 degrees. Here, with the one without anchors, it fails by debonding, the typical failure mode, debonding of the sheet away from the surface. and here you have some pull out of the flange, so debonding to fan plus fan to sheet debonding. You know, so debonding here was prevented and delayed. And for the ones with the other diameters of dowels, you can have here debonding of laminates locally between the top and the bottom here, but it happens at a later stage in loading. And this one here again debonding of laminates, but also at a higher level of loading. Now what I want to say here, that we did not apply load, we applied displacement control. The beams were applied, you know, were tested under a displacement control at a load, or at a displacement of 2 millimeters, or I think 1 millimeter per minute. These are the load deflection curves of the specimen. This is the control. This one without the anchors. This one is with 12 millimeter anchors. This one is with 16 and with 14. You can see that the increase in strength was dramatic between the control to the one without anchors, but you can see it failed at a very low midspan deflection, so the ductility is very low. We are able with the anchors to change the structure from a brittle from failing in a brittle mode at around 325 kilonewtons to a slightly higher load, but look at the ductility the beam is possessing before or exhibiting before failure. This means that I changed the failure mode from shear to flexural. So anchoring the ends of the sheets by splay anchors in a very simple method, it will enhance not for you the strength, it will also enhance the ductility. And you can see here that the 14, there is no direct relationship if you increase the diameter of the anchor to the strength. Why is that? Because you are increasing the size of the hole, so that will reduce maybe the strength of your specimens. So basically we find that the 14 millimeter diameter dowel is going to be the optimum for this structure. And these are the experimental results, a summary of it. You can see here all the loads they failed at, you know, at higher loads compared to the control. And you can see here like 287 to 103, 192 to 103, 89. Where is this? I'm sorry, I'm talking about the ultimate load, 317, 331, 365, and 342 compared to 146, which is a huge. So basically we are doubling the shear capacity, more than doubling the shear capacity of the beam in respect to the control specimen, and we are enhancing it with respect to the unanchored specimen up to 15% if you are using anchors. Our aim is not only the strength and the ductility. The ductility was increased significantly, and the strains, according to the code shear design provisions, the ACI, it won't allow you to reach to exceed the 0.004, which is like around 4,000 microstrain. You can see here that all the three sheets, the anchored ones with the dowels, exceeded the 4,000, and this one even like what with the 16 it was 5,000. So basically we are utilizing more of the strength of the material, and basically we are able to reach the limit of the 0.004, which is related to the aggregate interlock in shear. Again, this is the results. This one is in terms of the loads, and we did not find a clear trend between the anchor dowel diameter and specimen's capacity. The difference is marginal, and also we are using a relatively an 85 or a good value for the embedment depth of 85 millimeter, and with the 14 millimeter diameter is considered optimum for this design. So enhancement in capacity might be limited by the choice of embedment depth and hole diameter. A slight reduction in capacity for specimen B16 is due to the increase in ratio of the hole diameter to embedment depth of the fiber, which was the same, which is 85. So basically you need a more embedment depth to achieve the same capacity. And this is in terms of ductility. You can see that that the 40 millimeter behave the best in terms of ductility, 3 times more than the control specimen, because this is shear, and about even more than that of the unanchored specimen. So very interestingly, that anchoring the sheets with splay anchors will enhance both the strength and, most importantly, the ductility of the member, and most likely is going to give you an indication of failure. So basically the beam is going to fail in a ductile mode rather than in a brittle and sudden mode. So in conclusion, shear strengthening with CFRP URAPs laminates enhances the shear capacity. However, failure is dominated by the brittle debonding of the laminates. Anchoring the URAP laminates with CFRP splay anchors delay debonding of the URAPs, improve the shear capacity of the unanchored URAPs, and significantly enhance the ductility of the beam specimen. And based on the results of this study, the anchor diameter of 40 millimeter of splay anchors was optimum with an embedment depth of 85 millimeter. And for future research, we conducted an extensive study. We varied the angle depth, the angle, the double angle, the fan angle, the angle of the embedment, and we also varied the diameter and embedment depth in an extensive study with beams with other, with a slightly modified cross section. This one we took it as a pilot study that based on it we designed a set of 20 beams that we played with all different parameters that will tell us investigate the effect of several variables on the performance of anchored FRP sheets in strengthening RC beams in shears. And by that I conclude, and thank you very much. If you have any questions, please let me know.